Hello everyone, thank you for having me. My name is Dr. Cheng, and I am going to speaking to you on the intelligent realizations of marine electric vehicles for controls. To begin, let's look at the content page. What I will do today is to give you an introduction, modeling approach, problem statements, flowchart, the model of the ROVs, and the proposed fuzzy-based genetic algorithms for the sliding mode control, simulation followed by some experimental data, and then followed by conclusions. Let's look at the introductions. Traditionally, the hydrodynamics parameters and the underwater behaviors of the remotely operated vehicles are identified using the lab-based experimental approach. So in order to find out the models, we need to use good facilities to measure the parameters of the ROVs. However, this is quite costly, time-consuming, and required, as I mentioned, test facilities. And not only that, simple, you need to calibrate and you need to have a very accurate scale prototype models in the testing process. Often computational fluid dynamics, which is a approach using the commercial software, has been commonly applied on autonomous underwater vehicles to validate the hydrodynamic coefficients as compared to the empirical solutions. So this is the UUVs and is a very streamlined body as compared to ROVs that is not so streamlined. So let's look at the model of the ROVs. So the modeling approach for these open frame ROVs is quite difficult to obtain the hydrodynamics forces. The reason the ROV is inherently nonlinear, highly coupled in motions, and very complex in shape as compared to the AUV that is very streamlined. So to obtain the hydrodynamic forces, standard planar motion mechanisms, in short PMM, is used. This is what I call the test facilities. As you can see, that is very expensive and it requires a large floor space and investment as well as the scale prototype, or it can be the actual prototype which is not that big. What are the modeling approach being used in the literatures or in practice? First, lab-based testing, or some they use system identification method using least square estimations or the software CFD. For lab-based testing, marine dynamics test facilities has been used, towing tank, free decaying pendulum approach, which is used to measure the hydrodynamics damping and the air mass, free decaying using the spring instead of pendulums, and the pulley systems. And you can see that all these need extensive data from experiments and sea trial, especially for the system identification process. Although the last approach using CFD is more suitable, but please take note that there's an error of sometimes more than 30%. So what are we going to do today? So for the problem statements, the error resulted from the nonlinear least square curve fitting and experiment was more than 30%. So the prediction of the reasonably accurate set of hydrodynamic parameters for ROV is therefore difficult. So we need to have a controller to overcome the varying model uncertainties obtained from different modeling approaches. Types of controllers. First, model-based approach such as sliding mode controls, H-infinity nonlinear adaptive control, and there's many others. Model-free approach, we know that it's fuzzy logic, neural network, genetic algorithm, and there's many you can find from the literatures. Here, we just propose the fuzzy GA-based sliding mode control, which will address the current stability of the GA optimizations of the controller design of an uncertain model. So the flowchart demonstrate what we are going to say or present today is first, we start with the CAD modeling using SolidWorks, followed by CFD, computational fluid dynamics, to determine what is the damping coefficient as well as the air mass using two software, Star CCM Plus and Warmix. Followed by a nonlinear ROV model, we use Simulink, and then we use Simulink and MATLAB to design the control systems. And then we perform simulations using the same MATLAB Simulink platform. And then we look at the time domain condition, whether is it satisfied. If not, we just repeat the process. So this is a very typical control system design process. So what is the model of the ROVs? Let's look at the system design. So these systems basically consist of few parts. Okay, one is the enclosure, the thrusters, which is the propeller motors, which helps use as the actuators for the ROVs, docking hook, which basically used to capture something. For this case, we are trying to capture the AUV inside the docking hook, and the DVL, which used to measure the velocities. And this design is 1.5 meter by 1 by 1.7 meter height, and it has a dry weight of 135 kilo, and the working depth is at least 100 meters. So we test it in a water tank, as you can see from these slides. So the Doppler velocity log is to measure the velocity of ROV, pressure sensor to measure the depth of the ROV, and we have the inertial measurement units is used to measure the position and angular position of ROVs. And there's the two USB cameras for underwater image capturings. And as I mentioned, there's the actuators, which basically are thrusters, and there's total of 6 connected to the ISO 6 thruster drive cards to control the speed of the propellers. So this is the control, this is the hardware that basically, which I try to show here, not to be too complicated, but you will see that all this is residing inside the ROVs and is controlled via the laptops with the GUI design. So there are a few sensors that I mentioned in the top. Alright, is located somewhere here. Alright, and the thrusters, and you can see the webcams. Alright, and the processor we used as the target PC is the Antenna 3 PC104 with the DAQ, which basically consists of the IOs. And take note that we are using the AC power supply, but we need to convert AC to DC in order to power the respective components, as you can see from here. So the reference coordinates on ROVs, there's two reference coordinates are used to describe the position of ROV in the Earth fixed coordinate and the velocity fixed. Okay, velocity fixed meaning that at the body of the ROVs, Earth fixed is the inertia frames. So the conventions, we have some standard conventions that are used to represent the directions or degree of motions in the X, Y, Z, row, pitch, yaw. Alright, and the velocities is UV, W, P, Q, R. And the position is X, Y, Z, phi, theta, and C. So the model dynamics you can see from here, alright, is a 6 degree of freedoms. I'm not going to very in-depth on that, but just take note that there's total max inertia matrix, centripetal and Coriolis matrix here, and the hydrodynamics damping vectors, and also the gravitational force and moment vectors. So take note that 6 thrusters that's being used to control the ROV in the 6 degree of freedom, so it's actuated systems, and you can have a linear and angular velocity vectors V and linear angular position vector eta, as you can see from here. So the kinematics is basically helps to determines from the body fix to the earth fix, and the J1 and J2 is transformations that is needed to do the conversions. What about the hydrodynamics dampings? D. Alright, so as I mentioned, we design the mechanical system using the CAD SolidWorks, and then we do a meshing, basically using the computational fluid dynamics software package, and then we need to do a volumetric meshing for flow domains, and we have to make sure that this ROV here is more, or the volumes that this ROV is being contained must be at least, I think, 20 times more than the size of this, in order to simulate in the water. And we need to find out what's the flow patterns, streamline props, and then what we do at the end of the day is to determine what is the damping force versus the velocities. And not only the hydrodynamics damping coefficients, we also need to find out what's the hydrodynamics at the mass. You can see that we are using the multi-surf software CAD for WOMIX, and this is the WOMIX results, and which we can determine what is the added mass for each degree of freedoms based on the design. Since the design is symmetric, so we can do half of it. And then we do the test, the model validation test for the heat, meaning that in the Z directions, and yaw about the Z directions. The experiment test was conducted in the laboratories, and this test is 10 meter by 4 by 1.8 meters. It is equipped with the overload crane to load and unload the ROVs. The sample rate is 100 Hz, was used to sample the raw data from the sensors, and then from the raw data we use a MATLAB script just to plot, and just take note that the sample count is equivalent to 0.01 second. So we have this model validation test, and we built a GUI using the PyQt, a rapid graphical user interface developments, which we show the sensor readings, for example the depth and the yaw angle or the heading, and this is the depth and this is the heading, as well as the two USB CAD cam that we use to see the underwater situations. And we have a joystick that helps to control the actuators, and this is the software and the hardware in the loop integration and testing. The heat model validation test, to simplify the model, ROV is not commanded to move in the angular directions during the test. So because we are doing a heat, meaning that we are looking at the Z directions, so hence the centripetal and chronosystems are not dominant, as the ROV is not performing the rotational motion, so it's just going to the heat. So the effect of the quadratic components of the hydrodynamic damping is negligible for ROVs, moving at a very slow speed of approximately 0.08 meter per second. So the resulting heat model for ROV can be simplified to as such. So you can see that this model is rather simple. It's a first order systems. M is the mass in kilogram. The Z subscript W dot is basically the added mass, and the ZW is basically the damping coefficients. And this tau Z is basically the actuator force or the thrust. We're trying to do the validations. We need to rearrange the preceding equation in metric form as such, so that we can use the standard least square approach to find out what is the gamma hat. Hat is the estimate, okay, and we use a recursive least square RLS to compute the added mass as well as the damping coefficients parameter ROVs. So the similar approach can be applied to the yaw directions. So the modeling results, you can see the hydrodynamics damping in the X, Y, and the Z directions. The damping coefficients is written as such. The XU refer to the linear damping. The XU with the absolute U refer to the nonlinear dampings or the quadratic damping coefficients. So the CFD determines the values or the data as you see from this table. And the experiment, because we are using the experiments just for the heat directions, you can see that there's only a single value for heat directions. Whereas for CFD, you can compute different directions, X, Y, Z, for the added mass. And WOMIT is one of the software that we use to compute the added mass. And the experimental data, we only have one because we are only determining the heat directions for the added mass. So you can see that we are not so close, but you can see that in the same directions. We also compute the hydrodynamics added mass. As you can see from here, you will see that the values obtained from the experiments for the yaw directions, damping coefficients, as well as the added mass as such. So there is approximately 50% errors in the damping coefficients, while the error in the added mass coefficients is not exceeding 20%. So you can see that the damping coefficients can be quite large as compared to the added mass coefficients. So hence we propose the fuzzy-based genetic algorithms for the SMC. So how this works? Basically, for the robust control systems, the genetic algorithm generate the solutions, the optimizations, and search problem relying on the bio-inspired operators such as mutation and crossovers. You can see that we have this ROV model thrusters as actuators to ROV, and we have a controller which called the sliding mode controllers. And with these sliding mode controllers, basically we have the sliding surface defined by S is equal to eta dot plus lambda eta. Okay, this is basically the sliding surface, and what it does here is basically trying to see that whether the sliding surface is equal to 0, meaning if it's equal to 0 means that the target or the desired position is achieved. With that, we need to use the output S and S dot into the fitness functions, where we go through the fuzzy inference to get the eta M, eta C1, eta C2 through these equations, where we go through the genetic algorithms for mutation and crossover to develop a new control law. And this control law, so you can see that first part will be the fuzzy logic, followed by the GA as part 2, and part 3 will be sliding mode controllers. So the perturbed ROV models, first you have the nominal models, and then plus the lump uncertainties. Alright, so that will be equal to the tau, and the control input can be written as input, which is basically minus, remove the nonlinear terms on the nominal model. And what we want to achieve is that using the control input, the V, which is the energy terms, which we can determine the V dot so that it is less than or equal to 0 in order to achieve asymptotic stability. So if the bar is chosen to be too large, the sign functions will cause chatterings. in the control signals due to the sliding mode controllers. However, if we select to be too small, the stability condition will not be satisfied. So this leads to unstable control systems. So the fuzzy logic is used to reduce the chattering phenomena by smoothing the switch signal and automatic controller gain tuning. So the proposed fuzzy-based genetic algorithm for SMC, so the elite selection in GA. So if the fitness of the new control input is greater than all the previous value, it will be the new elite. So the sliding surface and its derivative are used to compute the fitness functions. So this is the fitness function that we use to compute, and the fuzzy-based crossover and mutation GA. So the crossover concept is that greater or further away from the sliding surface its derivative, the greater the variations, okay, between the offspring and the parents. So conversely, the control input will be less or remain constant if the system dynamics is within the sliding surface. So it's within the sliding surface, that's a good thing. So the control input will be less or remain constant. So if it go beyond the sliding surface, means that there's error, and then you will find that there's greater variations between the offspring and the parents. So for example, the tuning coefficients are chosen to be large. The tuning steps from generation to generation will be large. Okay, vice versa is chosen to be small. The tuning step will be small. And that will enable the system dynamics to diverge quickly, becoming unstable. So you can see that the UGA old refer to the previous generation, the UGA new refer to the newly created offspring. So for mutation, the idea is that the mutation will be adjusted according to the gap between the sliding surface and the system dynamics. So if the control effort is unable to achieve close to the sliding surface, the mutation will force the RV dynamics to maintain nearer to the sliding surface. So the offspring after mutation operations can be expressed as such. So the adjustment of mutation operation from the fuzzy inference mechanisms. So if the mutation will be adjusted according to the gap between sliding surface. So if the control effort is unable to achieve close to the sliding surface, which means S equal to 0, then the mutation will force it to happen. Okay, that's the whole idea. So the evolutionary process, first step, establish the fitness functions. Choose from the initial populations. We increment the uncertainty up to 20% of the nominal RV model and 1 meter per second of underwater current disturbance. So then we evaluate the fitness values and select the elite. And we start the fuzzy crossover operations. And if the fitness function is less than the specified fitness functions or fitness value, then we proceed to the next process and go to the step 8 and say we can compute the control signal. So if not, we have to start the fuzzy mutation operations. If we go to step 8, we compute the control signal, it will be treated as a parent of the next generation, as is the most appropriate chromosome for the current situations. So let's look at the simulation results. So launch and recovering, in short, LAR of AUV using the docking hook. So here what I mentioned in the first few slides, that this ROVs is trying to dock the AUV, means that try to capture the AUV inside the cage. So the scenario is such. You can see the AUV is at the distance away from ROVs. This ROV with this docking hook is trying to capture the AUV, the distance away from parent positions. And you can see that these unmanned surface vehicles is used to launch the ROVs. And this ROV will then be used to capture the AUVs inside its docking hooks. Okay, so this picture just show how the launch vehicle look like at the outside. So for simulation model, we are using Simlink, and basically it consists of the RV model, thruster, controllers, and there's a common filterings, basically used to estimate the positions. And once we detect the location, the direction of AUV, you will start the whole operations. For LA, the launch and recoveries, scenario 1, meaning that if the AUV is at 5 meters and the yaw is 45 degrees, so you will see that this is the AUV and this is ROV at the distance at 5 meters, at the distance away from the ROVs, the yaw angle at 45 degrees, and this is how we try to simulate whether we are able to capture the AUVs. And the position response as Z is equal to 5 meters, the yaw angle is 45 degrees. You can see that there's a good steady state response for that control at 5 meters, stable roll and pitch response, and is able to maintain 45 degrees heading for position response. What about velocities? There's a small velocity perturbations, meaning that it's not creating a lot of problems in the position control. and the roll and pitch response is quite stable. You can see that the magnitude is quite small. And what about the scenario 2, when y is 3 meters, z is 5 meters? So we are trying to move in y and z direction in order to capture the AUVs. So the position response at y equals 3 meters, z is 5 meters. You can see that y is actually able to achieve 3 meters mark, and the z is 5 meters, and the roll and pitch is also quite stable. The ether or the yaw, the heading angle is 0 because it's trying to maintain. We are moving the y, we are not rotating the ROVs. There's also a small velocity perturbation. As you can see, the value is quite small and the roll and pitch is quite stable. Let's compare the two scenarios, first and second, as to this tree. So you can see that y is 3 meters, z is 5 meters. The heading angle is 45 degrees. So are we able to control that? So we can see that there's a wave and current effect that we always use to simulate the ROVs is in the real situations. So the ROVs you can see here is able to dock the AUV at a distance away. So the position response at y equals 3 meters, z is 5 meters, and yaw angle is 45 degrees. You can see that the y is able to achieve 3 meters, the hip is able to achieve 5 meters, and the yaw angle is 45 degrees. And same, the small velocity perturbation, as you can see, the roll and pitch response is quite small and self-stabilizing. However, we need to do some robustness tests to simulate the proposed approach, fuzzy GA side mode controller, in short FGA SMC. So we have to carry out at different perturbations. The control system is tested to 20% or 1.2 times the nominal ROV model under the current underwater speed of 1 meter per second. So we try to test it out at a set point X and Y at 0.5 meters. So you can see that the position response that we plot this at different perturbation from 0 to 20% at an increment of around 4%. The position response indicate quite robust behavior to changing perturbations except for the hip, roll, and pitch and yaw angle at higher perturbation. So at higher perturbation, you will see that it's not able to withstand the kind of underwater currents. For this case, velocity response was plotted, and you can see that it's robust only at low perturbations, while in higher perturbations, only 2 of the 6 DOF display behavior of robustness to uncertainties. So you can see that when you reach higher perturbations, the velocity response is not so stable. And what about the robustness test tool that we compare the simulated proposed methods with individual SMC, fuzzy logic, and PID at 20% perturbations. So we are using all these parameters, which is all the control parameters that you can see here. And the last one is the proposed parameters that we have. And then we try to compare not only our proposed method, we compare with other methods such as even the PID SMC or just the fuzzy logic alone. You will see that the PID has a larger steady state error as compared to all controllers because it's not a robust controller. On the other hand, the proposed approach exhibits less chattering phenomena as compared to SMC alone due to the fuzzy inference mechanisms that have been used in the evolutionary procedures. As observed, the pitch and the roll angle is small and quite self-stabilizing as compared to PID. So this is the velocity response. And in summary, the SMC, PID, and fuzzy logic controller exhibit less robustness to the perturbation as seen in the overshoot, meaning that it overshoot the steady state values, and the steady state error is higher, and there's an oscillatory response as you can see as compared to proposed approach. So let's look at the sea trial results as compared to simulation that's target what we want to do. So the sea trial was conducted near Singapore Armed Force Yacht Club. So Singapore is at the map here. So we are at the north side, and this is the place which we call SAF Yacht Club. And the launch and recovery installation on unmanned surface vessel. So these are the vehicles that used to launch the ROVs, and we have to install the ROV onto the crane of these unmanned surface vessel. The test will perform using the warehouse main power followed by using the USV generators, and the LA was extended fully several times, so we have to check whether the crane works, okay, and we have to check whether the docking hook works as well. No mechanical abnormalities were noticed during the test. the laptop was able to communicate with ROV, or we call this as UUV docking hook, during the test. The LA was tested again in water, and the AUV DH swayed slightly due to the waves. No mechanical abnormalities were observed during the test. Both dry and water tests passed the verification test. So the result for sea trial, the docking hook actuator test, followed by the open loop control test, and the closed loop depth control and heading controls. So the docking hook actuator test, the linear actuator was S10, and we try to retract to be sure that it's able to capture the UUV. So we're just testing the two linear actuators controlled by the pulse wave modulation signal from the antenna tree, which is the PC104, to the two-stepper motor at the drivers, which is used to open and close the docking hooks. Then we do the open loop control test using the GUI interface, and the open loop search and sway test. So we're trying to move the ROV in the X directions, and then we also try to capture the velocity in X, velocity in Y, as well as the position in X and the position in Y. And then we measure the depth sensor at 0.5 meters, and it's roughly around 0.5 meters, and they know that all data are sampled at 100 Hz. And then we do the heap test, meaning that we submerge the ROV into the depth of around 2.3 meters, and the roll and pitch angle are quite stabilized. Alright, so you can see that the depth is about 2.3 meters, and the roll angle and pitch is quite stabilized, meaning that it will not roll or pitch. So this is roll and this pitch, so it's quite stable, and it's submerged to the depth of 2.3 meters. So we also do the heading test. So we are checking whether it's able to yaw approximately from certain angle, let's say 165 to 140 degrees, and the roll and pitch angle will maintain within a small value despite of some wave that's been disturbed on the ROVs. So we are trying to move further from the aft, right, and then perform the yaw test. So the yaw move from 165 to 149, and the roll and pitch angle is quite reasonably small. So when you try to yaw, there's no large roll angle or pitch, so you just yaw from a certain degree to 150 degrees. And the AUV DH was the next thing we try to do is to test the closed loop depth control to 0.6 meters, and then we also try to compare with the PID controllers, okay, with the following parameters and the proposed parameter, as you can see from here. And how we do that is basically we perform the same approach, trying to submerge the ROV to a certain depth. As you can see from the picture from the left to the right, you can see that the ROV disappeared because it's being submerged inside the water. And the PID tends to follow the wave perturbations. However, the proposed less oscillatory, you can see from the blue color line. So there's a slight steady state error of approximately 0.7%. The roll and pitch will maintain at a very small value despite the external wave disturbance. The results show that we can robustly position the ROV at desired depth despite the uncertainty and external disturbances. So this is the roll and the pitch angle that we plot. Not only for the heap or the Z-axis control, we also look at the heading control for the proposed controllers. Same thing, we also compare with the PID. You can see that we're trying to rotate the ROV in that's about the Z-axis. Alright, so the yaw angle basically settled to steady state with a slow response. Similar behaviors can be seen during the simulation as well. And the blue color is the proposed controller, whereas for PIDs, we are not able to achieve the steady state values. And despite the increasing proportional gains that we use, we still have about 15 degrees in the yaw angles, because you can see that we can actually increase the gain to reach the 45 marks, but the PID could not do that. Although the PID has a faster rise time and settling time, the proposed controller fared better in terms of the steady state yaw angle despite sluggish response. The sea trial revealed that ROV could maintain the desired yaw angle and the depth despite the model uncertainty and external disturbances. So with that, I would like to refer you to some of these publications related to the work that I present today. IEEE ASME Transaction on Mechatronics, Journal of Marine Science and Technologies, Ocean Conference, and these are the related publications. And with that, I'd like to conclude, it's important for ROVs for underwater recovery operations. A robust controller rely on a less accurate model can therefore be used to achieve acceptable target position and response. Systematize the process for realization of ROV model for control system design, and that's very important. And lastly, I want to acknowledge my students, MPhil students, industry partners, Jinjie Lim, Wei Yang Go, Mr. Leonard, Mr. Lim, Mr. Alvin, and Vincent too. And these are the pictures that we have taken during this trial. And with that, thank you very much for your